Oh, hello there. You guys, what's going on? Memes here. We're back. Another computational working session on our Higgs boson essay. You bring up a recent thing. Let's share it with the class, and we shall continue onward. All right, let's see how far we can get. Blah blah blah. We're gonna animate hype music in the back. Blah 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 blah. And where did we finish? Okay, we have our errors. Right. Basically doing the same thing, and I think we got to all right. So like H R, we computed it the other way, setting this equal to one, putting joule seconds because we're dividing into the reference of action. It appears to come out as one, so if we solve for that, you return again a value of 125.37 GeV divided by c squared. This should not be surprising. This little symbol down there for coherence. The fact of the Planck mass in its denominator. Oh, that's okay. Now we need to go through. Okay, we've done it. Cleaning it out. We got that, so we're going to continue here. Okay. So what we're going to do right now is this is the computed from our model here. Lambda represents the this little wavy thingy here. Is this the Higgs self-coupling strength? I kind of stole that from Wikipedia. That's because I can get very involved, but it's I find it fascinating that we had this theoretical framework set up. The link to this paper was at 2005, and we hadn't even turned on the Large Hadron Collider yet, so that's pretty awesome. All right. All right. All right. So this yields the value that we get from our standard. Dave. All right. Now, returns. Aren't aren't best measure returns our current best fit based on measurement. Okay. However, three significant digits makes it hard to find a potential candidate or a closed form representation, the Higgs coupling. We now introduce our of calculated value of the Higgs mass to correct out a few more significant digits. All right. So go from this. We'll keep everything the same. This is measured with surprising. Eight digits on this. This is pretty amazing. So we're going to put in our value for the Higgs mass in energy. 125. Let's see. What do we have for max? 76. Yeah, and I'm gonna have to label all these because okay, 125.376 with an error of 2 GeV. The value of the Higgs G. That's what we're putting in. We're putting its mass energy. 25.376 GeV. Go. Enable dynamics. What? This is what we get. Oh, we got two more potential significant digits. I don't know. Is five enough? Less than infinity, so see what happens. All right. Our expression. Okay. Pull that up. Okay. Move this down. Uh, oh, oh. Save as. So many notebooks. Sorry. Sorry. I'm keeping track of the journey. And again, could just be a whole bunch of hogwash. Again, open to that. Jen, I'm just trying to computationally reduce what we know, or we at least believe we know, into the simplest factors possible. Ooh, there's a little shiny thing by my head there. All right. Move a little bit so it's. Wait a minute. No, no, whatever. It's all right. It's all right. On the wrong way. There we go. All right. Mirrored things. Always confusing. Save as. It's cloud. There we go. That thingy there. And now we're actually getting into some more interesting things that I've been rambling on about as much, but could potentially explain a lot again. More data is required, and uh, there's some interesting things we're going to get into. So we might actually touch upon our quote unquote spherical god cow. It has as physics monastery fractal faculty Rick DeWitt had said before, some may call it utter speculation. It's so silly. It's weird that Dugan's like, what do I call it again? It's like, oh, bovine boson. I don't know. Hey, you gotta enjoy the little things, right? But oh, you got that. All right. Maybe I should actually share this out. Continue to those stuff and things that. God, what the heck did I do? How many things? Uh, wow. Just even going to a general page. And people still seem to be getting a little bit of a kick out of that Einstein joke. It's like, wait a second, Einstein was a real guy? All this time, I thought he was a theoretical physicist. That totally stole it from somewhere else, but on Dr. Hossenfelder's video about Einstein proved right again. It's like, wait, he was a real guy? At least I was able to make a few people laugh. All right, where are we? Where am I going again? Oh, wait. Oh, yes. Fill the stream out. There it No, I'm not telling anybody else to do that. I'm just doing it myself. You can interact with this media however you would want. Again, I ain't your dad. You do you, boo. All right. At least put in my little tucked away corner in the restricted section of the Wolfram Institute. Or any other place they let you put. And again, don't. A lot of times you'll see folks, and it's very interesting because I feel like a lot of stuff on the internet, like if you go to a bar, your bartender occasionally becomes a default psychiatrist, which again, seek professional help if that's what you need. But I think a lot of folks just like to be heard. And as long as I think somebody's at least listening to them, people will share a lot. Oh, somebody. Oh, wow. People that I view as very smart occasionally seem to be getting a kick out of these videos. So, good. Ooh, glad I could help. Where is these? Oh, God. My little, what do they call a section? Computing the Higgs mass, little root of action. And the spherical God calc. Uh, I mean, what else do you call it? It's invoking the spherical cow for something colloquial need no. If there ends up being any there, oh God, God help physics. Yeah. Again, it's physics. Same discipline that brought to us the tortoise coordinates for black holes, which may or may not use literal turtle shell for its notation. I love it. I love it. I get a little snicker and stuff. And the big thing is, if there is some there, it's like, do you want to call it the blah, 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 all these exponents, blah, confusing? No, what is that calculation? The spherical God. Oh yeah, yeah, the Higgs boson or God particle. Oh, doing this literal spherical cow. I'm sorry. I'm sorry. I'm terrible, terrible human being. All right. There. Throw in a bit of this monastery stuff. All right. Uh, Something over in the banter. I'll have to look at that later. There, put that there. I don't think anyone else really cares about this. If they want to check a working session, they can. Yeah, I don't need to spam working sessions anywhere. There we go. All right. Well, okay. Let's continue here. Okay, so we've got our numbers. Now, we got a few more significant digits. X. This should be okay. It is computable, so cool. But these few extra significant digits, we search for a potential closed form, which we may attempt. Where I can occasionally, oh God, spelling was like my worst subject. That and penmanship. I don't think they even teach that anymore. Do people know how to write? Oh God, I'm not sure I know how to really write in the traditional sense. And a close form with we may attempt to tell a story. All we literally do is we take these digits in here. Let's leave that there. Search our full results. Okay, so all we need is potential close. Okay. Out of all these things, what seems to be, okay, number one, what seems to be the most simple, computationally reduced expression that also matches the data to the best we can? And over 54, that matches for like four significant digits. 4 pi over 97, all right. 4 is 3. 33 pi over 800, 10 over 77, log, log 1/8, minus 1 plus z squared. Okay, it's got four significant digits. 4 pi over 750, all right, let's get 3. 3 over g sub g e. That's Gelfand's constant by chance. And Gelfand's constant is quite interesting. We'll get back to that. Oh yeah, it also matches all five significant digits. You include the zero, but we don't always give zero significance. So 4 minus that, that's 3. That's the Robbins constant or the something four-dimensional something, or four digits, okay. So out of our initial brief, and again, I looked at a lot of these and I just skipped them over. Why? Because never saw any significance of this. So I kept looking and looking. And again, a lot of this is just questioning myself. No, I don't have a story for that. I have no idea what might be going on. I kept looking. And long story short, after adding in fake digits, like what you can also do is you can just go to like another digit there, like do that. Because if you only have so many digits, a lot of times what I'll do is I'll add in fake data. because sometimes it won't always display. Like Wolfram Alpha runs a particular algorithm looking for likely closed forms. Again, that likelihood is probably also based upon things that people actually input. So sometimes I'll usually do like, if I need additional data, I'll do like 2, 5, and 8 for the next significant digit. And look, and sometimes I'll give you some more things. Like here, we should actually have a couple more that actually match for 5. Again, you just know you're inputting data, you have no idea. You're just trying to get more potential information out. Okay, we see a lot of the same things. Let's go down. Hey, look at this. I mean, that would have fit. That wasn't in the other data set, but now it's trying to match the 5. It's trying to match that. Yeah, 81 over 625, that's going to assume that it looks like a close form, but if that was the end of the line, it's pretty sure there's some more decimal places in there for our measurements, so you've got to account for that. So yeah, we got a few other potential ones, but that long story short is a lot of this is just me reiterating things that I've done. After going down so many Wolfram holes, so to speak, down so many dead ends. Again, I'm not Stephen Wolfram. Stephen Wolfram would have a very specific plan to leverage computation to explore all these paradigms. Stephen, in my opinion, is a good physicist. I am not a good physicist. Um, just some dude kind of LARPing on the internet. But if there's one thing I've learned from some live action role playing and occasionally some fans, especially within either monster or anime communities, some of the stuff that fans put out, chef's kiss. It's beautiful. Some of the animation, some of the stories. I'll pay homage to the original work. I'm sorry, I'm just rambling. The long story short is this, this, that just made up some data. Okay. That's about a potential close. If I really want this in a computable format, I know. Run. Dun, 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 dun. This is why I play anime music in the background. Oh God, that's so terribly ugly. No, no, thank you. All right, select content. Oh, just for anybody that was interested, I believe the current standard model prediction of this value is 1. Again, but the measured value is basically about 0.13 or 0.129. So basically, the things we have before is if you go to Wikipedia, you're going to find those values, or at least that's what I found there. And then you can delve more into the actual papers and stuff. I get these formatted. Excuse me. Yes, no, thank you for catching that. Hold on. Yes, that's a good point. Let me actually double check my audio and everything. Now, what happened is I usually I usually use the mic built in because for some reason two things with the same manufacturer don't always like to work together. One of my earbuds conked out, and I thought the other was still working. I even pulled it out, put it back in, but no, it since it didn't work, it just cut out the audio completely. So that was a good catch. Let me make sure. Oh, right here. Let's see. think it seems to be working. All right. Okay, so as long as I actually speak up and I might get freaking hair out of the way. All right. Okay. They're going over there. Okay, so what happens when we put the Z-bows on is that thing instead of the Higgs? Good question. We get uh, instead of outputting that 1 joule second. So the claim is, and again, it's just using the Wolfram data, and then we went a little bit more the other way. Plus that approximately 1 joule second, about 10 to the 7 erg seconds. Again, I claim a very underappreciated, depreciated unit. So if you put the top quark in there, it gets you close. It seems to be the closest one there. Is basically I'm just doing the hat of this gives you a dimensionless number in respect to the strength of gravity because oh, big G, the Newtonian gravitational constant, it's the exact same thing as h bar c. So if you take h bar, the elementary unit of action, multiply it by c, you get this is where you actually have a board. This is it's, it's right here. They just did a little dimensional analysis thing, and again, this just seemed like magic when I watched Thad do this before. But H bar is basically you get a mass, P mass. You got the P, so Planck length squared, and then that's over time. So it's a mass area rate. These are its dimensions. You can multiply it by C. C is just literally Planck length, minimum of length, divided by Planck time, minimum of time. That ends up equating out into P, so Planck mass. You get an extra dimension of Planck length, so it goes to length cubed, or Planck time, T sub P, where basically this is equivalent to big G, except that big G has Planck mass downstairs in the denominator. So that's why ultimately we're doing the same thing. We're comparing it to a value of uh, the Planck mass squared, I believe. We're comparing it to the Planck mass, and we're just squaring this term. So we get 2 units of mass. The Z boson, we get 1.8904 joule second. So again, it's since we're oh hold on, I forgot to share it again. There we go. Okay. So basically, when we do this with the Higgs, we get this, which is again, this was one of the early ways I found it. It has a slightly different expression, but basically it was 1 joule second. So I'm like, what if I assumed it was supposed to be one? And then basically, since it gives you a one there or gives you a value close to Planck's constant, we're just dividing it into that. So it's going to give you out the reference dimensions. If we assume it's one, then basically we get the same answer as we did before. But again, we're just still literally relating it to the Planck mass through our expression. The top quark gives you about a little over half a joule second, about 0.525 joule seconds. The Z boson, I believe, is the next closest. Yep, gives you 1.8904 joule seconds. I think a lot of this, rather than seeing 10 to the minus 34 or something, it's just one, one half, a two-ish value there. But at least for an observer like me to try to computationally reduce it into a way that makes sense. Because the thing I've learned, and a lot of this came from feedback from Anastasia and Shiloh, I can go up there and talk all those numbers, and they just look at me dead in the face, and Anastasia's like, "You've done this several times. I still have no idea what you're talking about." And again, you could be completely right and be talking about all these things, and somebody just doesn't understand. The thing is, you've got to keep it simple. You've got to explain the story, because if you start throwing around all these numbers, it's some people might just go there and be like, "Oh, okay, okay," and then some folks will just be like, they're so confused, they just kind of nod along, and they've kind of checked out from the conversation and end up going somewhere else. Um, the big thing is communicating it. So the reason why I'm doing this is in a way to kind of, oh God, I don't want to use the term normalize, because normalize assumes setting it to one. Although in this respect, I am literally kind of setting it to one, or that's just what pops out. So um, it's the interesting thing. And again, why should this be the case? Right? Why should it literally come out to the reference dimension? There's a little bit more into that, and that's I'm going to need a unit analysis piece in this as well. I can cite my original essay. Yeah. Is this just what you do? You just write something so you can just go back and cite your own thing? Well, to be fair, I think in order to justify anything in this essay, we're going to need to go back, and that original essay was probably required for it. So let's go back again. Okay. Right. It's a lot of folks like a bunch of folks seem to like to watch this on Twitter. I know she'll occasionally watch from both. Um, that's I'm working on computational essay. I don't expect there to be lots of folks here and everything. If that's your thing, or maybe you just want a little bit of scientific ASMR, that's fine. I'll occasionally, heck, I'll even listen to some of those AI channels if they just have a long thing that's just reiterating already known things, as long as it's a nice, soft, quiet voice. So I don't know. I tend to prefer humans again, human centric. But all right, so we did that. That's for the W boson. That's about 2.4 joule seconds using this hack. The electron 6.02 times 10 to the 10, which I tried to find Avogadro's constant connection there, but we're off by like 13 orders of magnitude. There's only three, excuse me, three significant digits there. We have the proton mass. That's about 18,000. The neutron, a little under 18,000 again. So put that in there as a one. We again get out our mass term, and again, we're finding 125.37 gigaelectron volts. If we assume that there is some there, again, if we assume there is some there, and that's why I'm putting in the computational essay model, just because I basically just write it as I talk, and again, it's a forum post, and I'm basically gauging it and attempting to channel my inner Stephen Wolfram, because if you read a lot of his blog posts, he could just write a paper or something, but he's like, yeah, I'd rather just explain it in this way and have all the links and the computational stuff. And he may have also had some personal thoughts on the publishing process, and he wasn't a big fan of basically refereeing somebody's paper and not letting you know who did it. Apparently, a lot of folks in academia got kind of perturbed at him because he would always sign his name on his work. I'm like, no, it's supposed to be anonymous. It's like, why would I be anonymous? It's you can take your human speculation there. Some folks would say, no, 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 we want this to be an anonymous process so people don't feel pressure. Then again, Stephen Wolfram's like, oh, why would I hide this? Some people may say, oh, there's something nefarious there. I don't know about that. Again, I can understand certain anonymity is because useful, but And again, there's also the old saying that nothing to hide, nothing to fear. Maybe, I don't know. But then again, Stephen Wolfram is not like a lot of other books. He tends to, Stephen Wolfram does what Stephen Wolfram wants. Kind of like a honey badger. I have no idea if anyone's ever compared Stephen Wolfram to a honey badger. That's not something I would expect to really say, but that's what came to mind. Okay. Our Higgs interaction value. Good. Let's take off all these crazy hold states. Get that box there. Okay. So we got these few extra significant digits. Now we're looking for a potential closed form for the Higgs self interaction that we may be able to tell a story with. And again, I know it's more complicated for this, but we're looking for something, at least me from a gamer perspective. It's kind of like if you're playing Magic the Gathering or Yu-Gi-Oh! Or Pokemon or something. Each card will have particular attributes and things and will be useful in different situations. So it's kind of like if you see something like that's 2 pi, it's like probably tell a story with that. That's the difference between Planck's constant and Planck's reduced constant, h bar. Some may view that as a cycle. 4 pi, maybe it's like a sphere or something like that. So we gain different intuition for what might be going on. So I'm looking for something, closed form expression that may have some interesting properties that we may be able to tell a story about. We'll leave it as this. Gives us properties. So if all right. So out of these potential closed forms, one actually hits it for all the digits. It does seem to be a very computationally reduced form. So continue our cursory search yields for candidates, but one only one unmatches all but all the given significant digits and has interesting closed form. What are we talking about here? We're talking about this. This is 3 over Gelfand's constant. What we're going to do is 3 divided by. Normally, it tells you on the bottom of the page and stuff. It may tell you more now. I usually, again, a lot of stuff was initially computed just because I didn't know what question to ask. Just on the Wolfram Alpha website, having God knows how many tabs open. Look at this, look at this. But long story short, that this G sub GE is Gelfand's constant. Gelfand's. So this, as we can see, gives closed digits. It predicts the next digit is 1, and then 7, blah, blah, blah. So, long story short, as long as we can compute, we can get as many digits as we want. We're going to use this as a form of a mathematical constant we can latch in on and, all right, we can take a step back and say, what if we assume this was true? And what we can do is, since we have this to basically X number of digits as we want, we have H bar set or defined at 10 significant digits now. The claim is we should be able to go back and more accurately calculate what the Planck mass should be, because ultimately that's what we're relating the Higgs boson to. Long story short is it is within the error bars. It suggests it's slightly on the lower end of the error bars, um, and towards a slightly lower value than what they have there. Not by much, but by just a bit. And again, who knows if that's right or not? Maybe there's other connections there. And again, there's a lot of speculation in here. Some of these things have an interesting relationship. Will it continue to hold? I don't know. We're gonna have to go by the experiments, the measurements, and see what we can figure out. That's science. I mean, imagine somebody coming on being like, "This is the science." Why? Because I said so. I mean, it's that kind of like saying, "I am the science." If you're gonna start sounding like a Sith Lord, it's like I am all the Sith and stuff like that. Maybe people should be wary. Just again, science is a process. It ain't a person. All right, so return that. What the heck is this? For the keen-eyed among you, you may have seen it. This is literally 3 over e to the negative pi. It's basically Yapfon's constant is e to the root pi. What does that mean? Oh no, excuse me, no, it's e to the pi. It's e to the negative pi, so that means it's in the denominator downstairs. Gives us this. So that's I don't care. All right. So at least as far as we measured, it appears to fit. Maybe it's maybe it's totally nothing. Again, it's rampant speculation on my part, but Gelfand's constant is interesting. Uh, Save. Save as. Takes essay 20. I'll save to cloud. No, I know. Totally exciting. Loading. Here we go. No, that doesn't usually pop up. So we continue. All right. Hey, Hanji. Oh, me? Um, I'm just some asshole. No, Massachusetts. Over in, I don't know. I think the shirt says USA, but you never know. I just East Coast US. So let's see. Ah, the touch. Oh, sorry. The Tishki. The Tishki. I apologize. I'm trying to the Tishki. Think I apologize if I'm mispronouncing your name. Welcome, Keishel. Good to see you. Popping in from all the different platforms. What's happening, Jax? Welcome, my friends. All right. We're going to continue to crank out a few more things here. Oh, Gelfon's going a quick tangent. So, do is let's search it. Gelfon. God, some of these things start coming up even quicker. You may have visited this site a few times. Hold on. No, it's constant. It's the exponential of pi. E to the pi, also called golf. It's constant. We go for math world. All right. Well, single dots, digits, blah blah blah. See that's kind of interesting. It's just giving the basic things, but Galfond's constant from Wikipedia is quite fast because let's embiggen this. Here we go. All right. Now I can even kind of rate it. Okay, it's exponential there. So again, e to the pi, the exponentiation of pi is equals e to the I pi raised to the negative I, or -1 raised to the negative I, which I had no idea. I think that's kind of cool. Uh, e to the pi apparently transcendental from alpha to set. Ugh. Oh, it's a Liouville number, blah blah. Yeah, people went over. But here's the interesting thing. E to the pi appears in relation to the volumes of hyperspheres. The volume of a given n sphere with the radius r is given by all of this, blah, 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 blah. Any even dimension to n sphere now gives this. So, long story short, summing up all even dimension unit hypersphere volumes and utilizing the series expansion of the exponential function gives e to the pi. This happens to be the sum of all even dimensional hyperspheres. But, but we have it dividing into three. That's not an even number. Why three? Not like we live in like about three spatial dimensions or something like that. I don't know. Would that be a clue? I mean, God, that would be crazy. I don't know. It's see, again, I just saw E to the pi. I'm like, I just went on to like the Wolfram thing, and I'm like, I see no significance in this at all. Maybe I should have looked a little closer. And then Robert Manager's got, oh God, however many constants. Oh, pardon. They show you the pi minus that. It's kind of 20. I mean, again, it's I to the E, also kind of close to it. Also, you can rewrite in the interesting things because I to the I, which that has in the hyperbolic partition equation that he uses to compute the fine structure constant. Um, this is you can rewrite this in very minor modifications, and then it pops out. Like the even dimension hypersphere thingy. All right. So how do I set? Just literally copy the expression. Uh, and real. Okay. The sum is that. Let's do our thing. Let's see. Go over here. All right. Mm, mm, ah. I mean, Jax, I mean, come on. It's not like people would just do things for money. I mean, if they did, listen, I got nothing wrong with somebody. earning an honest living. Just be open and transparent about that. It's not like people would fake that. Think that they're a righteous fighter to fight the good fight, and then if they actually had the opportunity to engage what they may have deemed as evil, uh, it's not like they're all of a sudden just going to go poof and vanish. Be like, that's not what I said. It's very simple. I just say we give our brave culture warriors what they want: legalize dueling and have them fight the good fights. You don't need to do that. Combat sports are legal in all 50 states. So I'm like, if somebody really has a problem with what we used to call fighting words, which I've heard people of all different persuasions use the same term, I pay attention when people that disagree on seemingly everything agree on one thing. Well, if it's fighting words, then I say we let consenting adults engage in mortal combat under the doctrine of bodily autonomy, or as Dr. Sarazawa said, let them fight. I mean, because, and again, nobody needs to fight. It's a consensual thing. I just think that people and their fans, I think people's fans and their supporters have the right to know who are the true believers and who are the talkers. Personally, I'm a talker. But then again, talking makes me thirsty. Hmm. But I digress. It's all right. I'm sure AI will end up modeling all of us at some point or another. One can only hope, dishope, one of those things, insert some persuasion. I'm not sure what to think of it. All right. So, Gelfand's constant. Oh, let's actually just type it in. It's constant. The Wolfram Alpha. Let's do let's do the definition. Let's see what it's got. Okay, we're just going to do the hypersphere. Let's see. We got to go back to our other little page we had there. All right. So we're going to need a blah, 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 blah. Infinite series of. I'm going to have to bust up the maths notation thingy here. Tools. Where is it? Thing. Oh, I'm so stupid. I didn't even need to mess around with AI. I just gonna create it a day. All right, still learning. Let's see, where are we? Patient, special characters. Could be maybe view. Insert types. Where's our math? Math. No, no, no. All right. Screen environment. Hmm. Assistant. Uh, um, I need to look this up. This, this is just something simple that's going to drive me insane. The Mathematica notebook math notation. Oh, it should be in the writing assistant. The thing I skipped over. Typesetting. Here we go. Here we go. All right. Obviously hiding. So, nation of that. So, need the sum. Infinity. N equals 0. Then we need okay, raised to the n. And then n. That it might be it. We get running, running, running. Incomplete count. Oh no, didn't work. That let me divide it. I normally just have it go downstairs. Where bracket, my bracket. Uh, it's not giving anything useful. Why is it doing? That's a piece of code. At least the code output. User error. Try this again. Actually, let's put this in here. See what happens. 0 to infinity. Is it doing it wrong? Must be the exponentiation of pi. Should literally just be this. This could just literally just eat the pie. Oh, that should work. Yeah. Yeah. Oh. Oh, look at that. Oh, that's pretty. Starts going up really fast. Eight. Wow, look at all these extra features. I didn't even know they were here. Oh, very neat. Unfortunately, I'm too much of a noob to know how to use those well. All right, I get that factorial right there. Wait a second. Uh, okay, we've been so right. I'm gonna I'm gonna need to take a quick tobacco break because I'm a terrible person. I'm gonna go crank one, and we will be right back. Let me get something fun for us. Something fun. Hmm. So that I need to do a little troubleshooting. Delete that. That's what we're supposed to have. It's constant. Minimize. Oh, oh, Eve. Let's find a quick little something we can share. Let's go to ah. Where's a good one? The short. So wait, that's thing. Scientific intuition. What is real? Like that. Is a philosophical size. I think it does a pretty good job. Theater mode, boom. All right, so we'll share this and we'll be right back after these messages. First, sharing this where we can try to be professional YouTuber. Show the tab with the audio. All right, we will be right.
You can reduce every statement in physics to statements that involve either no dimensions or mixtures or sets of these five. That's it. So the goal here is to try to put together a story that accounts for all the actual measurements we've made through all the whole history of physics, right, or a whole history of humans so far, to identify the built-in features that are fixed into reality. So that's very clearly statements here. We are assuming the constants of nature are accurate measurements of built-in features allowed in physics. Okay, so we're taking that as the starting position. And now what we're trying to do is we're trying to come up with any sort of logical model, a geometric based structure. It has to have explicitly specified logic. And we want to find the simplest possible logical model that contains and explains all of those features. Okay, if that simplest model has other features, cool. Whatever happens, the simplest one that can contain the features we know are real. we need to, at minimum, account for all of those. But by account, we really mean deeply. You can't just account for something by just reproducing it. That reproduction needs to be some sort of action, some sort of story, some sort of insight to the structure of what's going on, not just, you got it right. That's what quantum mechanics does, right? It gets it right. in a way, like statistically, but it didn't really give you insight to the structure of what was getting it right. So we're trying to get past that. And we're not starting out with an intuition of exactly what the universe is supposed to be. I mean, we've all done that. I've done that. I wrote a whole book to try to fine-tune my intuition of what it must be and fine-tune my collection of the details I have to keep track of and account for. Okay, but at the end of that book, I ran into a wall. The main thing I tried to focus on was trying to visually, or without reducing dimensions, track the action of gravity. Right? That we have exact equations from general relativity for what gravity is. And I wanted to not have to take a slice and then understand those equations a slice at a time. I wanted to find some way to more richly understand them. And the method for doing that was to introduce a notion in which space-time itself, the metric itself by which everything is being compared, is actually quantized, so that there are other degrees of freedom that allow the metric to mix. Right, there's a whole bunch of bubbles that can move around, but it gives you available density gradients and all the fluid actions that we characterize in fluid mechanics. Okay, the problem was that although this separation of the metric itself gave us density gradients, which actually perfectly map to the logic of warp spacetime, they didn't give us an explanation in the end. Once we were mapping space-time's warping curvature, that mapping didn't then give us a next step of insight that said, and now I know why the boundaries we made up or imposed on the situation in order to have that kind of structure exist. You follow me? So we got to a position where we found if we come up with a condition where we impose this different kind of metric of space-time, one that's quantized and has parts that can all mix about and so on, then we can reproduce the same sort of effect. But the goal when you have a model like that, when you have so much you're just assuming, is that you don't really believe the model until you kind of tweak it to make the fit that you were looking for. But that tweaking and that fitting should then automatically be fit to a whole bunch of other parameters you weren't actually trying to tweak it to. So that's the situation I ended up in. It didn't give me any insights for how quantum mechanics would be coming out of the same sort of model. And more damningly, for me, logically, is that once we got to the end where we could actually explain general relativity in terms of that same different sense of metric, that explanation didn't extend naturally in any way that I could see to the effects of quantum mechanics. So it was just fine-tuned. It wasn't powerfully revealing. So what we're going to do is instead, we're going to back up and not assume whatever model you're currently assuming, what the space is infinite, or that it's spherical and infinite or finite, or cubic and infinite or finite. Those are common visions. We're not going to assume a certain geometry. What we're trying to do is focus on the measured transforms, or the measured built-in facts of reality, and find some way to make sense of them. So first step is to list them, or to become aware of them. So the physics track go through beginning to high-end courses is it tunes you into the investigation humans have had so far using measurements to look into reality in new ways. Look into reality in ways beyond what you can do just with your hands and your eyes, using tools to look further into the structure and precision of what's going on. Okay, so in that process, people have discovered that they can model actions using equations, and some of those equations, most of those equations, have strange scaling factors that relate things to each other, different parameters like as time or length and space, right, to each other, but with huge scalings. So it's not a one-to-one conversion, but there's a conversion. Okay, so the first thing to notice is that there are conversions between the different parameters of reality. So I guess even before that, 5 dimensions right, than just what the shape of reality is. But we have 5 different bases, different actions by which we can make a reference in this story already. So that's the starting position. Those measures, times, space or length, charge, temperature, and mass. All right. This is very, very fast, But the major point here is that these 5 bases, these 5 dimensions, form a network of logic that account for all the transforms and exchanges we've found or just seen so far in physics. The things we're trying to account for. We're not trying to account for ones we haven't seen yet. Okay, so all of them. That's a really amazing thing. You can reduce every statement in physics to statements that involve either no dimensions or mixtures or sets of these 5. That's it. Okay, so there's 5 ways to make unique measurement in the world, or 5 unique dimensions.
All right. I apologize that we had a new mic. It was obscenely crackly. I tried to minimize the ear hurt, the mustache. We threw out the mic. We went back to the old one there. So, uh, let's see. There are we? All right, back to action. Oh, Share. Boom, boom. Should probably actually make sure I'm not all that crackly myself. Oh, I Higgs essay. Let's go back to blah, blah, blah. Okay. All right. Seems to work. All right. Or restart my anime music that was running out. Okay. I'm just gonna take this. I'm gonna do another window just to make sure this actually works. Me, let me do the. Mind me, I'm on another screen right now. Infinity n equals 0 to the n raised the n, and it converges to Galfond's constant. All right. Okay, let's do that. Run it. Oh, looks a little better. Okay. 0. That'd be the gamma. Okay, something's wrong. Be the sum of the n. That's. I love how there's the exclamation point on the infinity. See if that will give you the right thing on Wolfram Alpha. The natural language. Of course, well, it came out wrong. Let's try the simpler expression. Do that. Let's just go to go throw this in. Let's try it one time. Uh, to infinity, yeah. It's rewriting this. No, it does converge. I'm looking at see, this is the thing that bothers me. What do you mean it doesn't converge? Need more parentheses, don't I? Let's throw a parenthesis there, there. Changes anything. It shouldn't be doing infinity to the units. I'm just gonna make it doesn't make any sense. Okay, so why is it? Okay, screw it. We'll just put in the Wolfram Alpha. Uh, I tried. I tried to look at the other way. It's Wolfram Alpha just seems to be more user friendly. It knows my mistakes. I don't. What do you mean? Wolfram translation found. I'm looking at it right now. Oh, God. Yeah, I'm literally just copying the Wolfram Alpha code. Okay, all right. Uh, uh, There we go. All right, all right. That took far too much effort. Yeah, it's again, Wolfram language is a wonderful tool set. Not perfect. None of us are perfect, but perfectly imperfect, I claim. Long story short, yes, it's giving us e to the pi. Okay. So delete e. Get this presentation. So subpod, subpod. Let's get the information we may or may not need. Partial sums, convergence. It converges. All right. So now we're going to talk about Gelfand's constant. All right. One of those things that just made it a little bit easier. There's that. Okay. Start. Set. It converges. There we go. All right. Um, um, save. Because and it just randomly close out. Yeah, yeah, it's good to save often, my friends. Uh, Take it. Peace. Do this. E E E or Gelfand's constant defined as e raised to the pi. Mm, E raised to the pi is also the sum of all even dimensional hyperspheres. And where did I get that from? The actual page. Where did I put that? So many. I got like 6 or 7 open. Uh, Unit volume. Hyperspheres. Of, how do they put it? Is the sum of all even dimensional sphere unit even dimension unit sphere volumes. Even dimension sphere volumes. Oh, I mean that sounds like a useful context if we think spheres are a useful thing, and apparently is in even dimensions. So G sub G or Gauffins constant is defined as e to the pi is also the sum of all even dimensional sphere volumes. Uh, the yeah, basically e to the pi. Some more stuff will be required there. All right. Save. All right. Cool. What do we got? Give me one moment. All right. All right. That should work. Yeah. No, no, no. It's apparently if you take an AirPod out, it just magically forgets everything. There we go. I swapped over to the other mic. All right, something, something. I guess it's open enrollment time. Okay. It didn't say spam, so let's make sure this is actually working again. Okay, it seems to be working. All right. Apologies for that. God. I see. I stand by. We should have the standard do not call list, and the owners of any entity that violates that, it should go directly against them. I don't know. I'm just saying, if corporations are people too, I believe the board of directors and the C-level executives should be their tribute. I.e., if a company does something that a normal person would be charged with, let's say, murder, we should charge the top level executives because they know what's going on. And this shouldn't be an issue because when you hear a lot of times from the boards of these companies, they're doing all the right things. And if they're doing the right things, there's nothing to fear. This is why I should never be Emperor of the United States. We continue. All right. So let's just make sure it's actually working. Okay. All right. So it does seem to be working. Okay. All right. Let's get the freaking hair out of the way and let's continue with our window. Our this one. There we go. Okay. God, I'm such a terrible creature. How dare I give people what they seem to be insinuating they want? I know. You don't like those folks, that's fine. They don't like you either. Why don't you get in the ring? Ba 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 ba. What? What? Oh. So when you say that this is the we must fight for our freedoms, by fight, you didn't actually mean get in the ring with folks. You meant speak words on the internet. Duly noted. All right. Thank you. Thank you. All right. I caught it this time. I caught it this time. All right. Rather than rambling on for the next 6 minutes and pulling a culture. Oh, I love you, brother. All right. Where? All right. So we got our converging thing. So, all right. So let's put a text. Our closed form expression is 3 divided by that, or 3 over e raised to the pi. It's, oh God. The pith root of e. Delicious pie. Okay. So what we're gonna do now is we're basically gonna assume this is true because it's pretty. Where do we have that? G. There we go. Not the General Electric G. Okay, our closed ring expression 3 over pi. Interestingly, is dividing the sum of all even unit dimensional spheres into an odd number. 3. Might this have something to do with our apparent 3 spatial dimensions in which we exist? This is an exercise for the reader. exercise for the reader and other smarter folks than the author. Author. Lex author. Okay. Save. Given a potential closed form for given a potential interesting closed form for the Higgs self interaction strength uh, we will conjecture that this is true and explore the consequences. In this case, we will leverage this closed form and use our same algebraic expression to back calculate what the what a more accurate value of the blank mass should be MP. I need another blank mass over there. Let's see. God, I feel like I'm it's you listen enough into when Stephen Wolfram is going over things and doing live streams. Very often he'll say, "Let's see," and then just kind of go and read. I'm like, God, I don't know. When you hang around certain folks, you pick up certain manners. Now, I'm I'm not saying that I may or may not have polluted the water with certain folks on perhaps certain platforms without saying. I'm just saying that just, occasionally, if you hear folks, and it's like, I'm just saying, I, now again, I'm not the first person to say that, but occasionally certain things, and occasionally the, certain things like, again, I was also not the first person to see different folks on the internet and be like, hail, fellow internet traveler, but I did use that very frequently in certain groups where it seemed to promulgate? Proliferate. It seemed to proliferate through certain communities, and occasionally I'd hear somebody saying, where did the term hail come from? And it's like, I stole that from Jensen Quinn, full disclosure, but I may certain folks popularize things. I'm sorry. I'm getting back into the deep lore of things that we don't need. Where I just see the plank mass. M sub P. Oh God, it's starting to get longer. Okay, Professor Sean Carroll. It's two R's and two L's. It's not two N's in there. Okay, so where did I put? Oh God, I have a blank mass somewhere. It's just M sub P. Where did I start putting that? Oh, here we go. M sub p. Here to the inverse Planck mass squared. Okay, so the mass MP. P. Should also probably have, okay, we'll worry about that more later. All right, all right, got that, got that, got that. Hmm. Okay, blah, 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 blah. Let's see. God, I'm doing it again. Uh, precise. Derive. Wow. Wow. I'm so terrible at spelling. So embarrassing. All right. With the Planck mass. There we go. Back to where we wanted. Okay. So, long story short is how we calculate. Okay, so this should. Oh God, how did I do the calculation? Because this has this. Okay, I need a different expression. All right, so file, save as. We do 26. It should be 27. Essay 27. I'll save as. Save to cloud. All right. We're slowly getting there, folks. We're slowly getting there. Heck of a journey. All right. It's interesting just because I know some folks here. I've known for a good while. We go back to some of my much more trolling days, and other folks have come around more recently. So hey, Poindexter. Speaking of coming around recently, thank you. Uh, 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 that's a software tester. I'm not basically. You could say maybe I'm a wetware tester. I'm just testing out this meat suit that I find myself in, or at least apparently find myself in. Who knows what's actually real? All right. Let's see. Well, that's the thing. It's certain spelling errors. It might not actually be an error. Apparently, what is it? I think Stephen Wolfram was happy at one point because when they had the term branchial space, it didn't kick up an error because there's something branchial as something to do with fish within their branchial skeleton forms or something like that. So let's see. That's just a random tidbit I think I remember from like 3 or 4 years ago. God, it's amazing. How does memory even work? I don't know. That's a question for smarter folks than myself. Okay, so now I need to go back and actually see how I did this. All right, so let's bring up another thingy. And go back to a window. Let's see. Bookmarks. Bookmark manager. So how did I do this? Hold on. I'll actually share with the class. What do we got? God, my massive list of arbitrary bookmarks about things that are at least interesting enough to create a bookmark from. Higgs and Gelfand's constant. Oh, that's it's in this dude. All right, somewhere here. Oh, good. Open all 22 in a new window. Yes. A dangerous thing, my friends. All right, so you don't need this one. I'll share this screen over here. Where are we? Window. Yeah, this is from a live stream, I think, before I left. All right, so it's not there. Boom, boom. All right, boom, boom. Boom, 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 boom. Okay, I think it's... Okay, so there... Okay, here's... This is basically what we just did. The conjectured Higgs self-interaction value using that number. We went down there. Found this guy here, Galfond, 3 over Galfond's constant. We have Galfond's constant. That was a top quark thing. These are conjectured values for other particles. Put up a little thing about those earlier. That's something that somebody wants to look at. All right, so I think we just need the mathematical formulation of the standard model. So let's embiggen it a bit. Okay, so I think this was down towards the gauge groups or something. Free parameters. This is where we are. Okay. So here's what we're going to use. Because this is basically how we computed this. So, so if we have the coupling strength, the claim is if this is true. Okay, so we did have to do a couple of steps. That's why. I'm sorry, my brain was just kind of lagging a little bit. It's all right. So if we have this, all right, so this is free parameters in the standard model. So if we have this 0.129 and we got a couple more digits, here's what we're going to do. We're going to set this thingy equal to Gelfand's constant, or that 3 over Gelfand's constant. Okay. We're going to leverage the Higgs vacuum expectation value that we had there, which is part of the Fermi constant, which we have to about 8 significant digits. So we're going to plug that in for maximum precision. We are going to... How did we do this? We're going to back calculate the Higgs mass. I'm trying to think the best way to do that. Did I do that somewhere else? Hold on, I'm just opening up. Did I actually even do this? This coupling constants. I did do this somewhere. Because I think oh god. Well, I guess it's a good thing that I'm slightly confused. Sorry, I'm just on another thing. Because if we calculate that, then we should better be able to calculate. How did I do this? Hold on. I'm just gonna do this right now. So the 2 vacuum expectation value, which should be okay. So what we're gonna do is we're gonna assume that's right. And then it should let us back propagate the Higgs. All right, so let's set this. So let's solve for x. That equals 3 over Gelfand's constant. You have to be careful of putting e in there because very often we'll just choose elementary charge. Okay, so that's all GeV squared. It's the same as I should just be able to rip out GeV. So just rip out the units. is our parabola. All right. So this gives us a Higgs mass again within our error bars. Can we eke out some more digits? Let's do. Okay, because this is where we got this from. Got 7 digits there. 7, and it's giving. Okay, 6. So let's take this as if it should be true. So if that is true, so then if this is accurate, okay. So I'll take this, we'll divide it. Now we're going to solve for x kilograms. Sorry, I'm just doing this just because it's faster, because I know I'm going to make some mistakes. All right, square that. Let's set that equal to, we want the dimensionless. We just solve for x. We're going to need h bar, because that's what we're making our base assumption from. All right, more digits. We want to get out to defined at 10 digits, so stop there. I just happen to know that 817 is the last 3 digits there. Okay. So it should be equal to this value here. Okay, and this is in giga-electron volts. Should give us a big number. All right, gives us a big number here. So this should essentially be the Planck energy. GeV, so GeV divided by c squared. Okay. More digits. Okay. And again, this only has so many digits, but why does this not look right? Let me check one thing. Go over here. Okay. I just want to see the difference between Thad's calculation, because it did deviate, I think, around the 6th or 7th significant digit. Okay. Let's take this value. Let's divide it into Thad's value. Just want to make sure this is the right number. Let's pull off kilograms. 10 to the minus 8. All right. So 1, 2, 3, 4, 5, 6. Okay, so if we include the 1, it's 1, 2, 3, 4, 5, 6. So it deviates in the 7th significant digit here. To be fair, 4, 1, 5. Okay, so it does start to deviate in the 6th digit, but it's pretty small. Okay. So this is all right, so this is what we get out from here. So seems to have pretty good agreement. Let's take a look at it versus just normal Planck mass. Where is that? This Fermi coupling, Planck mass. All right. Let's grab those digits. So it should be the lower end of that. Okay. So I'm just going to throw this in here. Let's divide. 6, 4. All right. So it's 2, 4 in there. So it could be 1, 0, and then we have 1, 5. Okay, so it does seem to be on the lower end there. 1, 2, 3, 4, 5. All right. Okay, so that does look correct. Or at least according to my knowledge. So it's just we're getting one thing and then we're just back propagating it and seeing what we get and how it compares. Let's see. All right. Okay. Okay. So I got that. Don't mind me chugging the elixir of life. And then cutting it with water. All right. Almost there, almost there. Don't worry. We're all gonna wrap it up. Okay. Make mass, pile, save. Because we can, my friends. All right. So, if this expression gave us, let's see, should be. Okay, so if it gives us that, here's what we're going to do. We're going to, might be a little bit different. We're going to solve for x. We're going to set equal to 3 over Gilfon's constant. So we're literally just, oh god, I'm not even sharing. I apologize. What a noob. There we go. All right. So here's what we're doing. We're just replugging this in. We're hitting enter. We're going to see what it pops out. This should be dimensionless. Okay, so it's giving us this expression here. All right. So then we're just literally going to take this expression here. Oh god, these 4. Just so it's all the other random jazz times 10. Times 10 raised to the minus 6. X squared equals 3 over Gelfand's constant. Okay. So it's doing its thing. It's giving us that value there. Okay. So let's see. Computable data. It's going to be a pain in the butt. Yep, it's a pain in the butt, so I'll just output the normal stuff. Subpod content. And again, we'll put this all in little pretty charts and everything. Just get our at least work out there now. Okay. So again, we had, was it 125 plus or minus? And again, just should note it gives a positive and a negative answer because it's an x squared. So maybe that's useful. I just put it on the shirt for the calculation as just so it would come out as a positive value. I'm assuming that there's some positive mass conjecture or something, but we should note sometimes what might seem as a weird thing, maybe it's telling us something. Was it? Didn't the rock or something say, "Oh, there's a sign convention here. Oh, it's probably nothing." And it's like, "Oh, okay, there seems to be some antimatter stuff." It popped out from the maths. Okay, so got all that jazz there. Okay. So we'll delete that. So again, that's only tweak the digits just very slightly. Okay, boom, boom. All right, so I could probably hide that in here. Let's see. All right. So then what we'll do is we'll replug that in, assume it's set equal to h bar, and then we'll just calculate out the Planck mass like we did. Okay. So delete that. Okay. Which yields an estimated uh, estimated Higgs mass of mass of all right. So put content and okay, down there. Roll it up, roll it up, roll it up. There we go. I know, I'm really just working with one extra. The significant digit change. Is that enough? Probably not, but oh, let's see. I mean, I just really just want these as two answers. Let's just take that out. Okay, boom. And output this. Boom. Should be second answer. Okay. Code. Boom. Boom. Throw you in there. Boom. Boom. Should give us our negative answer. There we go. Okay. Roll it up. So we got our answers. Positive and negative. Just so we're being precise. Let's hide that dude in our. Hide him in there. Roll it up. Okay. Might be 4, 7, but then again, it's like we only have so much digit precision anyway, so. All right. And again, that's what error bars are for. File, save. Okay. All right. So, plain text. All right. Again, we return with a positive and negative value for, again, full disclosure, for both a positive and negative value because of the x squared term in our expression. This time, a slightly smaller value still within our error bars of 2 for the sixth significant digit. File, save. Now we insert this value into our original expression for relating the magnitude of the Higgs mass to the Planck mass to the squared magnitude of the Higgs mass to the Planck mass, assuming it should be equal to the magnitude of h bar. Okay. I'll save. And we solve for x. Okay, so what we do is literally our original expression, 125.375. GV squared divided by x kilograms equal to h bar divided by joule seconds. Okay. So now this was normally the Planck mass, which we were scaling that by. We're going to pop it back in. Very slightly more information. Let's see what we got. Oh, I'm like, oh, that's not correct. Oh, squared. Oops. All right, this looks like it might be a little bit better. Let's see. I was going to say, I don't recognize that number. I did something obviously wrong. All right. How many digits did I need to put in for that? It's just giving out the Planck mass. How do I get it for some more digits? I'm going to need to probably put out... I have to put in more, aren't I? Okay, so we've been going over for 2 hours. This is a tomorrow problem. We'll figure it out then. Okay, at least we have the general expression set up correctly. Now we'll just try to eke out, and maybe we'll just be honest, like we're throwing in additional digits to see what will pop out. So at least kind of worked over there. Okay, so what we'll do is, God, edit, undo, edit, undo. Edit, undo. Edit, undo. Edit, undo. There we go. Okay. So, yeah, more learning is required, but, God, okay, so we can delete this guy. That's at least putting out the blank mass, so we'll see if we can maybe massage out a few more digits after that. Okay. Solve for X. Alright, so one last time. File. Save as. It's going to be number 28. Higgs SA 28. Okay. File. Save the cloud. And we'll publish the cloud. Alright. Do 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 do. Mana mana. Do 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 do. SA save as. Alright, saved. File publish to cloud. I forgot to do that. I had to read it going after I left. XSA 28. Publish. Copied. All right. So for anybody, awesome one. Here's the thing. I like to think of the Higgs as a smiley little thing. Maybe we just needed to use like a little smiley face that Walmart used to use because, well, obviously you're smiling. It's a the more things change, some things just seem to stay the same. So we'll put that there. I'll throw it in the link in the doobly-doo below. I think that's what we got. So let's see. We should just quit. All right. So thank you everybody that's joined for today and that may temporally watch in the future. I understand it's not always the most entertaining thing watching a noob like me try to hack away and try to put something into some coherent words, but hey, I got a lot of other stuff. My level up shirt from One Punch Man season 3 is not season 1. I, I don't know what I say. Season 1 was one of those like I it was just so good. It was so good. I'm like the bar was so dang high that I'm like I really don't know if you can beat that. It just had so many aspects, the music, the animation, the derpiness. Oh god, I'm still gonna watch it and stuff, but it's like again, I'm just gonna take it as it is. I'm not gonna worry about it. But then again, actually, what I started to do is I'm going back and starting to watch the English dub of Daima, Dragon Ball Daima, just because a lot of the animation in that is very beautiful. So that's the thing. That's okay. Mostly, I was just wearing this, and since I'm just a working session, I'm allowed to be whoever I am. So I guess that's allowed. You can be yourself, so to speak. So with that, my friends, take care, y'all. We'll catch y'all on the next time, and stay safe, everybody. Peace out.